In compression spring stress part 1, we investigated force and stress profiles. Let's move on to the calculations. To recap, our spring has at least 3 states, with the spring operating between min and max working lengths. When we consider stress, we need to look into the worst case scenario load cases, and this is because the spring will fail unless it can withstand this degree of loading. So we need to focus on the max and solid lengths here. Okay, so first we need some inputs. So let's define our diameters and spring index. Next, we need a solid and max working lengths, solid and max length force, and free length. And finally, we need the material. Stainless steel with a tensile stress limit of 35% and a UTS, or ultimate tensile strength, of 1950 megapascals. Let's start with the stress occurring in the wire across the cross-section at max working length. Stress is torsional only at this stage, so stress equals 8 times mean diameter times force at length divided by pi times wire diameter to the power of 3. So if we plug in our variables, we find a stress of 648 megapascals. But in part 1, we discussed both shear and torsional stresses occur at the wire cross-section, and we need to account for the highest stress occurring at the spring ID. So we need to apply a stress correction factor here, and WAL is one of the most popular factors. WAL, K, is calculated using the spring index, C. K equals 4 times C minus 1 over 4 times C minus 4 plus 0.615 over C. Application overlays shear against torsion, resulting in the reduction of stress at the OD and an increase at the ID. And this all occurs as we need to make correction for the curvature of the spring. So let's add this to the stress equation. Stress at the max working length is recalculated as follows, with K applied as a multiplier. Stress increases to 685.26 megapascals here, with the use of the multiplier. In our inputs, we indicated stress needs to remain under 35% tensile strength. So let's check this out. Dividing stress by UTS, we can see stress remains under 35%, while the inclusion of stress correction takes us over the threshold. So if we look at the results on their own singularly, we need to reduce the stress, or we need to consider alternative materials here. We should consider an alternative grade of stainless steel or an alternative as shown below. But for now, let's just continue and check the stress at solid. First, we input our new force variable into the stress equation. We find a torsional stress here of 809.94 megapascals. The WAL stress correction factor remains unchanged, and with the focus on finding max stress at ID, we add the multiplier to the stress equation as before, and the stress increases to 656.71 megapascals. We need to go back and check the stresses against the material tensile strength, and if we look at the results, we can confirm stress has increased in both cases and is far in excess of 35%. Although we don't work at solid length, manufacturers will compress the solid if set removal is required, so we should definitely consider an alternative material grade. Whether we add stress correction or not, we can check our minimum working length is at most 80% compression. Previously we have checked lengths, but we can also calculate using the stresses we have calculated here. In both scenarios, the chosen maximum working length is appropriate and the geometry is acceptable. To summarise, stress at solid length is 809.94 megapascals without stress correction and increases to 856.71 with stress correction. At the max working length, stress is 648 megapascals, increasing to 685.26 with correction. At the max working length, we go from 33.23% of the tensile strength to 35.14 with the correction factor. The 80% compression check is included here just to sanity check the geometry, just to see if we are following the 80% rule. At solid, we go from 41.54% of tensile UTS to 43.93 with stress correction, and in both cases we are way over the threshold. Across the two compression spring stress videos, we have learned the basic maths of stress, checked force profiles, looked at wire cross-sectional stress, applied stress correction due to curvature using WAL. We have also used some inputs to assess a design.